Yeah, this one. So before I review the small signal, just quickly review just the large signal current. I think so. If I take a NMOS and apply a gate voltage and just show that as and then you can apply a so this is your gate to source, drain to source, and source to bulk, right? And if I measure the current flowing through the drain, then for so obviously the first region of operation is what? VGS less than VT. It's cut off, right? But we saw yesterday that it's actually not cut off. You are in subthreshold and you actually have very little current, but the gain is actually very high. Gain means you change the VGS a little bit, the change in current is much higher than actually when it is on. Okay, it acts like a BJT. So cut off or subthreshold. And then second is if VGS is greater than VT and VDS is really small, then you're in the region what's called linear resistor region. Typically books don't say that, they just say triode region and this thing, but this is actually in analog a pretty useful region. So this will be ID is approximately equal to mu n Cox W over L VGS minus VT times VDS. Okay, so it's a linear relation between ID and VDS. With that constant, actually, it's a voltage control resistor. So you can change VGS to change that resistor there. Okay, now the third one is if VGS is greater than VT, but VDS is not small, but it is less than VGS minus VT, which is called VDSAT, V on, V effective, V excess, a lot of names, but that's what it means. Then the equation is a triode region equation, which is a nonlinear equation, which is mu n, write it so that I can, ID equals to mu n Cox. You can write it as 2 or mu n Cox W over L and then divide by 2 at the end. Okay, so that's the triode region, and I just write this fourth one right here. So fourth one is VGS greater than VT, but VDS is now greater than VGS minus VT, and then ID is equal to a constant current. Okay, constant current, but there is actually a modulation, especially you've seen yesterday in your simulation, when you took the channel length to be 0.15, the variation was actually quite a bit with VDS, right? So the variation was, so so in reality, you have this lambda term, which actually varies with VDS. If your length is small, then the lambda will be large, okay? So that lambda is inversely proportional to length and directly proportional to current. So if you want a large R out or RDS, then you want either a longer length, not either, you want a longer length and smaller current, okay? So that's what gives you a larger R, okay? So that's for NMOS. And if I just draw a small VDS versus IDS, then for different VGSs, that's the curve. So this is this linear region here, before cutoff, obviously there's no current. And then this is your, sorry, yeah, the linear resistor region, and this is the triode region, and this region is your saturation region. Okay, so that's for NMOS. Okay, so these equations you should, slowly start getting very comfortable, and that's what you'll be using. Even though a lot of these equations are invalid nowadays, it's still a great tool for doing hand calculation or, you know, just a first order calculation. Okay, so now I'm going to show you the the PMOS one. So in PMOS, it's kind of all flipped upside down. So your gate voltage has to be lower than the substrate voltage to turn it on. Your drain voltage has to be lower than the source voltage for the current to current. So everything is kind of negative. Okay. So, but like I said, yesterday or day before, um, when I started designing, I kind of just took all the mods, which then just looks like the NMOS. It's just mu P, VTP, VDS instead of VSD and so on. Okay. But at least you should be very comfortable with the direction of the current. Like yesterday, I saw people just substituted the NMOS with the PMOS. You do that, it's all off, right? It doesn't work. So that's why the PMOSs are always referenced to VDD. So if you have a VDD, so NMOSs, here they were referenced to ground. PMOSs are usually referenced to VDD. Okay. So if you have a PMOS here, so it'll look something like that. So you've seen the symbol actually, which has the bubble and the arrow as well. Typically, you either find the bubble or the arrow. Actually, I like that because that way at least you shows you, you have a PMOS. So the bubble actually is good because that makes the two source and drain terminal symmetric, right? The arrow tells you that, okay, that's the source, but it's not physical in the sense. So then as a designer, you want to make sure whichever is your source, you want the arrow to be in that direction. Okay. If you flip it and actually it's not an arrow, it's nothing is wrong. You'll pass LVS, it'll work fine. It's just confusing and it's not a good way to, kind of do the schematic. All right. So, I think the bubble one is probably better, but in analog, you use the arrow one because it tells you which direction the current is flowing. Okay. So now here, excuse me, the gate to source voltage is negative, right? That's VGS or VSG. If you want to write it as a positive quantity, then VSG. But your voltage is, this is positive and that's negative. So your gate to source voltage is a negative voltage, or a source to gate voltage is positive. Okay. And then your drain to source voltage is, what's my, and your drain to source voltage is also a negative voltage. I'm sorry. Well, yeah, you can. Yeah, it's probably better. Let me think. Yeah, it's probably better you put it as, otherwise it'll be confusing. So this is actually, this is VDS, but it is again a negative voltage because your ground is on the source, which is actually VDD. So let me just maybe put it this way. Okay, so that again is VDS, but VDS is also a negative quantity, and the current flows in this direction here. Okay, so now, so that's VDS. All right. So the condition, if you want to preserve the sign, if you want to preserve the sign, then the condition here would be VGS greater than VTP is cut off, because VTP is a negative number VGS is a negative number. So you take two negatives, then it has to be greater than that. Okay. Then second condition is, if you want to turn it on, obviously this is cut off for subthreshold. Okay. And the second condition is it is turned on if VGS is less than VTP. Okay. And VDS is greater than VDSAT, VGS minus VT. Because these are all negative numbers right now. So if you preserve the negative numbers, then the sign just everything the greater than and less than just they flip. Okay. So we can take an example. So for example, the 0.18 you're doing, it's the NMOS is what? The VT is 0.5 volts, let's say, around 0.5 volts. The PMOS is probably minus 0.5 volts. Okay. So if VTP is equal to minus 0.5 volts, that means in order to turn it on, VGS should be less than VTP, or in other words, VGS should be less than minus 0.5 volts. Or so for example, in this case, the VGS needs to be, so minus 0.6 is, for example, less than minus 0.5 volts. Okay. But if you take the magnitude of this, so you say, oh, I just want to do magnitude, then VGS is 0.6 should be greater than the magnitude of this. Then it just looks like the NMOS. Okay. So if you preserve the signs, all the equalities inequalities flip. If you take mods, then the inequalities become like NMOS. So when you're reading literature, typically they'll never do mods because just to keep it clean, or if you're reading papers or textbooks. So that's why it's good to sort of know this. But when you're doing your own calculation, like when I do my calculation, I just always, even today, I just do VGS greater than VTP, VDS is greater than VDSP sat and all that. It's just like in my head, I know that it is all flipped. Okay. But if you have to write a paper or a document or anything like that, then you have to be very clean. Okay. And do that. I mean, I've seen people write papers with mods too, but just be aware of that. Okay. And same thing. Then if I need, so let's say VD sat is equal to minus 0.2 volts, then I need VDS to be less than minus 0.2 volts for it to be in saturation. Okay. So for example, if it is minus 0.1 volts, it is in linear region. If it is minus 0.3 volts, then it is in saturation. So it's all flipped. Okay. So just be so I'll write the equation in just with the signs, but just, you feel free to kind of follow whatever you're convenient with. Okay. Like you just want to do mods and do it with NMOS style, that's good, because that's, even today I do that. Okay. So that's your, this is your linear equation. And if VDS is same thing, if VDS is really small, so let's do the second one, the same one. So let's say VDS is really small, then ID P, let's say for the PMOS is mu P Cox over 2 W over L. And if you want to preserve the sign, then it is, actually it's still VGS minus VTP square, because VGS will be negative, minus of VTP will be positive, and that square will still be the same thing. Okay. So it's still VGS minus VTP wholes, sorry, this is the linear mode. So VGS VTP times VDS. Okay. Got it? All right. And if you preserve the sign, then obviously the negative cancels, and IDP is the direction of the current flowing from the source to drain. That needs to be positive. If you do drain to source, that needs to be negative, and then you need to flip it. Okay. So that's why just follow one convention you're comfortable with and just stick to that, for at least for your own design and this thing. But you should know the direction of the current which is flowing. So PMOS, you remember the source is always on the higher side potential, gate is always lower than that, drain is always lower than that. On the NMOS, opposite. The source is always on the lowest potential, drain is higher than that, gate is higher than that. So just, at least know that from the circuit sense, and then you do. And same thing now, the third one is VGS less than VTP and VDS is, so this is the linear mode, which means if you preserve the sign, VDS is greater than VD sat, and then that's the linear equation, which is same equation again, say IDP mu P C ox over 2, sorry, there's no 2 here, 2 W over L, and then 2 times VGS minus VTP, VDS minus VDS square over VDS square. Okay. So it still holds because the signs will cancel, get squared out, and you'll still get the current either in the negative direction if you're doing IDS or positive direction if you're doing ISD. Okay. And then the fourth one is the saturation one, which is VGS is greater than VTP. Still less than VTP, and VDS is less than VDSat, which is the negative. Mod will be greater than that, and IDP would be mu P C ox over 2 W over L VGS minus VTP. The internet is slow. Square, and then lambda times VDS. Okay. So basically same equation, it's just that your lambda is going to be different, mu P is going to be different for the PMOS. So typically mu P's are 2 to 3 times lower than mu N. So that's typical. So in the newer technologies, they're actually pretty close. So mu N is typically 2 to 3 times, not 2 minus 3, but 2 to 3 times of mu P. Okay. So that's why the NMOSs are always preferred when you're trying to do high-speed stuff. But actually, for audio devices, we always try to use the PMOS because the noise is lower. The low-frequency noise for PMOS is lower. Okay, noise we probably won't be able to cover in this, but I'll maybe just give you a overview next week. Okay, so clear now the large signal analysis. Everyone is clear. Okay, all right. So yeah, what's that? Yeah, so the question is for audio device, why do you use PMOS? You remember yesterday we did a common source amplifier, like you had NMOS with a current source. The low frequency noise is dominated by that first device. Okay, and that low frequency noise comes from, you remember when we did the VT derivation, we said there's a metal, there's an oxide, then you have silicon, right? And then in the last step of the VT derivation, we said, oh, actually the charges in the oxide is not zero. There's always some impurities trapped inside it. And those impurities are actually mostly in the interface. Because what happens is you take a silicon, and the way the silicon dioxide is done is you actually just heat it to a large temperature, like 1,000 degrees, or I forget how much. Actually, it's there in the West Australian, so it's around 1,000, I think, or maybe 1,500. And then you pass moisture on it. So it starts oxidizing, okay? And then it becomes silicon dioxide. So that's how you grow silicon dioxide. Now, once silicon dioxide is formed, the oxidation happens pretty well. But the first layer which forms with the silicon itself, that is still very sort of nasty. So that's where the charges get trapped. And because of that, what happens is those charges kind of affect, it's almost a quantum effect where they seem to release into the channel and grab from the channel as a low frequency noise. So as you go lower and lower and lower frequency, the amount of charge which gets released and trapped as a noise increases. Okay, and that's what, for low frequency, that's what is important to us. So there are various ways to reduce that. There are one of the brute force method is you just make the channel area really large. If you make that large, that average just reduces. The other techniques are, there are some circuit techniques where you actually switch them. So you kind of switch them fast that all the low frequency noise gets canceled between two devices. That's called chopping. Okay. But PMOS is That's the reason PMOS is involved. Even in RF, where the frequency is really high, but when you down convert the RF to voice band, that low frequency noise is also important, and you tend to use PMOS because of that. Okay. So, but for speed wise, we always almost prefer the NMOS because of the mobility. The mobility is almost 2 to 3 times higher than PMOS. Okay. Clear so far? So that's a large signal model. For NMOS, it's the same equation as PMOS, just the current and all the voltage are just sort of flipped. Okay. All right. So now that's the large signal model. And yesterday we went at length to describe um, how to linearize a nonlinear device or a nonlinear system about a bias point. And the reason we linearize it, first of all, our system analysis tools are for linear systems. Second is we need linear systems. So, for example, the amplifier we've done, that is, we want a linear amplifier. We don't need a nonlinear amplifier. And maybe I'll quickly go through that just to show you why the linearity is important in that. Okay. So remember you did that NMOS experiment where you did a diode connected, applied a voltage, swept this, right, and measured ID versus which is VGS or VSD. But the reason you did this configuration is to make sure that it is always in saturation. So then that way you just use the saturation equation. Okay. And if you remember the VGS versus ID curve, what I drew just in the previous slide, this one is VDS versus ID for different VGSs, okay, get to source voltage. Here what I'm drawing is VGS versus ID, and the VDS is also varying with VGS, but it is making sure it is always in saturation, okay. So then you're plotting ID versus VGS, right? And then the curve looks at around VT, it just kind of goes on a square fashion, okay? And the whole small signal model is basically trying to, so this is a nonlinear curve, which is that ID equals to beta times VGS minus VT whole square. And what we are trying to do is we're going to say that, hey, we are not actually operating in that entire range. If my circuit is actually operating very close to some bias point here, then I can linearize that area and get a linear model for it with some error. And that's what we did yesterday, where you took a diode and we said we linearized it by doing a Taylor expansion. And then we said we dropped everything from all the square, cube, and the fourth order terms. We just kept the linear term, and then we did some calculation that, okay, to what value of the input, how large or how small is the input for which this model is valid. Okay. Now, what did I say yesterday? What do you think? So you do a small signal model. How small a signal it has to be for the model to be valid? You remember we discussed that yesterday? Yeah, there is, sorry, go ahead. Yeah, so you remember I told you that the small signal model, that's like the biggest confusion with people. And you say, oh, I linearize this model for small signals, right? How small a signal? Yeah, KT, gate people will say it's KT. Your voltage or everything needs to be KT, and that's absolutely wrong, obviously. Basically, that's saying that it is the smallest quantity available in universe. And obviously, that's a ridiculous number. So the answer is, there is no answer saying that there is an absolute number for it. It depends on what your application can tolerate. Okay. So like I said, you're doing an audio amplifier, then you're doing for a high fidelity system, then you can tolerate very little nonlinearity, right? If you're doing it for just for like phone or some, like a speaker, like you have these tiny speakers just for even the speaker on the phone, you can tolerate more nonlinearity in it. Okay. So that becomes, and I think, so today what I'll do is, yesterday I showed for the diode, I'll quickly show for the MOS device and show you, why it dependent on the size of this thing. So let's take a point around, so we bias it to some point ID. So let's call this ID 0, for which you have VGS 0, right? Now, if I write this equation, it'll be ID 0 equals to mu n Cox over 2 W over L VGS minus VT square, right? And forget the lambda part right now. That's we're just going to talk about just the GM part of it. So forget that part right now. And then we say if you linearize this area, because the ID to VGS relation is a nonlinear relation, and we said, okay, now what if my VGS is a very small number? Okay, and so I bias it to some DC, and I say I'm going to vary the VGS by a small amount. And what's that factor? So we said, okay, so then I can just take this bias point and sort of find the slope around this, which is basically saying take the Taylor expansion and find the first linear coefficient for it. And, or in other words, it's a partial derivative. It's a partial derivative because here there are three things which are varying, right? VGS, VDS, and the source to bulk. So you fix everything and vary one and find out what's the variation. Then you fix the other two, change one. So yesterday we just did two. We didn't do the third one because typically we don't use it. So we did the variation of the ID versus VGS, and we did the variation of ID versus VDS, and that was your R out. Okay. So let's look at just the GM part of it. So this, if I do it, this is the term which is called GM, and this becomes 2 times mu n Cox, and the mu n Cox cancels. So this one becomes mu n Cox W over L. So yeah, 2 times this and 2 will cancel. So I can just write mu n Cox W over L VGS minus VT, right? And then we said, as a designer, you kind of reorganize this, and a useful expression is 2ID or ID 0 in this case, the bias voltage over V on or V sat or whatever you want to call it. Okay, so I'll kind of mix match it so that you get used to it. Because, all right, so that's a useful quantity because usually these are the two variables given to us. Okay, fixed current we are biasing at, and we have a limit on the current, and this is the headroom. It's like you remember yesterday when you're sweeping the current mirror is only valid after a certain VDS, which was equal to this value, right? So if I'm designing an amplifier, I say, oh, your output cannot go lower than that because that thing collapses, right? So that number is a useful number for us, and ID is because we are given usually a certain amount of power we can dissipate. So we do that. And if you remember yesterday, we said that the other quantity which is really useful is this GM over ID. So for this one, it will be just 2 over V on. Okay. This GM over ID, this ratio tells us if that device is actually in subthreshold or linear, saturation region. Okay. And, I showed you the subthreshold current equation. It looked like almost a BGT, which was exponential. So when we design, we are going to always do a operating point, and we'll have a, XScheme has a nice way where you can measure something in the operating point and actually display it on the thing. So we'll always have the devices we care about to be in saturation or region. We calculate the GMID and always displaying it, because when you're changing values, you'll be thinking, oh, I'm just going to increase this W by X because I want to do something. And suddenly the GM over ID goes from 6 to 15. And if you wanted it to be in saturation, you want to backtrack that back. And same thing the other way around. You wanted it to be in 2025 to keep it in deep subthreshold. And then suddenly you started changing things and it went to 6 or 5. And then you want to move it back. Okay. So we'll print it and make sure it is the same. Okay. So now the question is, by linearize, if we didn't linearize it. So now let's take an amplifier, right? The common source amplifier, which it did yesterday. So I'll just put a resistor, linear resistor. So we have some RL, and actually, you know what? I'll do a PMOS so that you guys start getting used to PMOS as well. So for the PMOS, I'm going to have a PMOS and I'll put a resistor here, RL, okay? And the voltage would be, I would have some bias voltage VGS, and then some small signal, which is my audio signal, let's say. Okay, so that's your VI. VI, and this is your Vout. And this is a negative gain, so this will be out of phase by 180 degrees, right? Because if this current is going down, the current is increasing here, this will go up. So it's 180 degrees out of phase. Just like the NMOS, PMOS is the same too. Okay, so now if I find out Vout is what? Vout is equal to ID times RL, right? And this is in, I assume that it is always in saturation. I bias it in such a way that is in saturation. Then ID times RL will be what? Mu P C ox over 2 W over L VGS P minus VT square. And here I'm just going to treat it as NMOS, okay? So in my head, I'm already doing mod. So you just bear with me for that. Into RL, correct? Got it? So now let's say this VGS is some VGS naught plus VI, right? The bias voltage plus the audio signal over that. And let's say VI, if I'm giving an audio signal, let's say 1 kilohertz signal, so VI will be some amplitude Vm times sine omega t, let's say, correct? Okay. So I'm giving audio signal on top of some bias voltage VGS0. So that VGS0 makes sure that you have some bias voltage, and then on top of that, I'm giving this tiny audio signal to amplify it to this amount here. Okay. So what I'm going to do is I'm going to substitute VGS to be VGS0 plus Vm sine omega t and expand that and see what happens. So I'm going to write now mu p C ox by 2 W over L, and this VGS will be some VGS0, which is your bias voltage, and I'll bring this VT on this side, so that's your V on, and then minus, plus Vm sine omega t, and then the whole square of this into RL, right? So the voltage here is this equation here, right? V out equals to ID times RL, and RL is obviously linear, and then, so this is the total V out, okay? So if I'm looking at the V out, it's sitting at DC, and as I give this audio signal, it's kind of amplifying it, okay? Got it? So that's the simplest amplifier, common source amplifier. It's a PMOS amplifier. Now I'm going to expand this. So let me call this entire term here as some quantity beta dash or something, okay? And this is obviously VD sat, right? And I'll call this V on for now, okay? And then I'll expand this. So if I expand this now, then V out is equal to, so V out is equal to beta dash V on plus Vm sine omega t whole square. So then that will be what? V on square plus 2 times Vm times V on sine omega t plus Vm square sine omega square t, right? So I'm just taking that square term and expanding it. Got it? Now, this part here, this beta times V on square, that's ID0. That's VGS beta times VGS minus VT whole square. So that's your DC current, right? So if I expand this, this is just ID0, right? This part here is ID0. And then I get this extra, the signal term, which is plus beta dash times 2 times V on times Vm sine omega t. Now, can you recognize this term here? What is that term? This one here. That's GM. So the GM was equal to mu n C ox W over L. That's 2 times beta times V on. So that's GM here. So that's how you got your GM. So that's a linear term for that. Then on top of that, you get this Vm square sine square omega t. What's the expansion of Vn square sine square omega t? What's sine square omega t if I expand it to without a square? The trigonometry relation. 1 minus cos 2 omega t over 2, right? So this one will expand to Vm square over 2, right? Minus cos 2 omega Vm square cos 2 omega t over 2, right? And then the whole thing is multiplied by RL, obviously, that even. So you got it? So you get the DC current and the sine wave Gm times multiplied by that. And this is all you wanted, right? You had the DC and you wanted to amplify that audio signal, but you have this term now. Okay? No, it's not noise distortion. It is dependent on the signal, right? Because this is related to signal, 2 cos omega t. But it's twice the frequency now. Okay? That's the harmonic, right? So you see in your audio amplifier, you get a spec called total harmonic distortion. That's the harmonic distortion you have, right? So you've seen how, when you guys have your rock shows or whatever it is, and they just blast it and you get this jarring sound. That jarring sound is because of this term here. I mean, you have 2 omega t, 3 omega t, and so on. So let's say I give a pure tone of 1 kilohertz. Now, if you had a perfect linear amplifier, the output should be also 1 kilohertz with a higher amplitude, right? But now you're going to get 1 kilohertz, then some 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on. And that's that jarring sound you hear when in your audio amplifier. Or in case of cell phone, that's your error. Okay, or because you have digital, everything is digital now, so you're not going to get distortion, but you're going to get error. So if a call is dropping, or you're not getting good signal and all that, that's because you have too much of this and it's not able to get the sound back or data back or whatever it is. Okay, so so now if I just expand this. So this is ID0 minus Vm square over 2. That's your DC term. And then you get Gm times Vm sine omega t. And then you get this term, which is Vm square over 2. Actually, I missed one. There is a beta. I have to carry 2. Beta dash here. So this will be beta dash here, and this will be beta dash here, cos 2 omega t. Okay? All right. And then the harmonic distortion or the non-linearity is defined as THD is total harmonic distortion is VM, so if your amplitude of your sine wave is, let's say, Vm or V1, and the amplitude of your first harmonic is V2, third is V3, fourth is V4, then the total harmonic distortion is defined as the RMS of all the harmonics, V1 square plus V2 square plus V3 square and so on. That's the RMS value divided by the amplitude of the fundamental, which is here, let's say it's 1 kilohertz, it's over there. So that's how THD is defined. Okay. And in this case, what would be the THD? It would be this quantity divided by GMVN, right? So if I take the THD here, it would be, forget the sign for now. So it would be Vm square times beta over 2 divided by Gm times Vm. Okay. And then you take that amplitude away and this square goes away. And then, you take Gm to be 2IdV on, beta is mu and Cox over there. You cancel all that. What you're going to get is your distortion increases as a function of your amplitude. So if your amplitude is really, really small, then the distortion will go down because this square term will become 0. Okay, so that's your total harmonic distortion. And we'll do a simulation in XSpice where once you design your amplifier, we'll put it in the main audio amplifier and measure it, right? Because there is a TSD spec for the amplifier, which is that commercial amplifier we have. So if you go to the data sheet, so if you go to the data sheet of the operational amplifier, and there's probably a plot. This is the gain plot you saw, rejection ratio, channel, yeah, TSD here. So it's TSD plus noise, but just assume that it is TSD. So you can see the TSD is like less than 0.01%. Okay, so it's actually pretty good. So so from here to 1K, 20K, obviously it kind of goes up at higher frequency, but lower frequency, you can see the distortion is really, really, really good. Okay, so what we are going to do is we'll do the basic amplifier, the differential amplifier, and we'll plug it in that system, give the microphone signal like 60, I don't know what's this measured at. They should have a measure like where they're measuring it. So typically it will be like 70, 80 dB SPL at a higher number. And we're going to give that same signal and see how much distortion you're going to get just from a simple amplifier. Okay. So that'll give you an idea because this is a really good number. This is almost hi-fi basically. Okay. So now everyone clear, right? So when people ask like, okay, what is this small signal model valid? Well, it's valid to whatever is your distortion. Like if you are trying to get 0.01%, this VM will probably turn out to be just like a microvolt or something, right? Once you plug in the values, we don't know what it is, but it will be, for this amplifier, it's not going to work. Okay. Once we make the amplifier high gain, put it in feedback, then the distortion will go down. But with this amplifier, you're not even going to get like 1 or 2% for anything, any small signal, like even for 1 millivolt. Okay. So, yeah. Resistance is a linear term. Yeah, I just took ID, but resistance is multiplied everywhere. That's my cursor. Okay. So the resistance is multiplied everywhere here, right? So when you divide this, the RL will cancel. Okay. So then you're just left with this term over here. Okay, because your nonlinearity is all coming from that current basically. So you got it now why you should be. So when you do your AC simulation will just show you this. It will not show you this. Okay, because the AC simulation, it's linearized and then shows you again. So you put 1 volt, 2 volt, 100 volt, it will show you GM times VM sine omega t. Okay, the nonlinearity, you're going to see this once you start doing transient simulation. So that's what we're going to do. We're going to give a transient wave for what the measurement was done for the op amp, and then do a Fourier analysis of the output and find all the Fourier components. So if you have given a 1 kilohertz, we'll find all the Fourier components. So we'll find the 2 kilohertz, 3 kilohertz, 4 kilohertz, and then we'll use this equation here. So we'll take the 2 kilohertz component, square it, 3 kilohertz, square it, 4 kilohertz, square it, add them all up, take the square root, and then divide it by the amplitude of the fundamental, and that will be the percentage. Okay, so we'll do that when you're doing the overall simulation. Okay, so clear now, small signal and why we do small signal and why you should be careful when you're doing small signal analysis or doing AC simulation. So AC simulation always means it's the linearized one. Okay, so that means it's about a bias point, and if your signal is varying so much that your bias point is varying a lot, then you have to rethink that. Okay, so this one, everyone is clear about this one. So, and then we went through the whole current mirror and the reason. Do you remember the two main reasons we want current sources or current mirrors? Because you remember when we do an amplifier like this, what's the problem of having a resistor? Hmm? No, source is here. This is drain. Well, yeah, don't remember something. I think you guys are remembering something which you have. There's nothing to do with source drain. Source is here. This is drain. So obviously that's not source. Yeah, exactly. Yeah, so this gain is this ID times RL, right? So if you want really high gain, you want a high RL, high output resistance, right? If you want a high output resistance, but the problem with that is when you do a DC biasing, even a small current, this output will just go. So for example, in yesterday's example, we took 200K, right? And 200K times, let's say 100 microamp is what? It's 20 volts, right? But your supply is only 1.8 volts. So there's no way you can bias it, right? So that's why the current sources, these are called active loads, okay? So these active loads actually decouple your DC biasing to your AC gain, your impedances, okay? Make sense? You guys just forget very quickly. Well, actually, you're not forgetting. It's mostly because you're browsing. Those people who are browsing are the ones who just, I mean, this is, I think we went at depth, but you guys are not able to answer at all. So that's something you just have to listen. Okay. You can't keep reading or doing anything. Got it? So just pay attention to the things I'm trying to emphasize. Just pay attention because these are the key things in design. So if you don't pay attention, you're not going to learn anything. Okay. So now it's clear. Okay, who can tell why we are using current sources or current mirror? Anyone? Okay, now I have repeated like 6 times now. Yeah, maybe someone else. Anyone else? So why do we use current source as a load, or why do we need current source? Yeah, so we are trying to get a gain, which is ID times RL, and ID is equal to the transconductor gain times the input voltage. But if I have a really large RL, then the DC bias I cannot control. Okay. So that's why I need a current source which can bias. See, current source is what? What is the ideal transfer function of a current source? That you put whatever voltage across it, it'll draw that current, right? Which means I can bias this to any point I want. If this was a current source, then the bias current will remain. And the small signal, that is for very small signals, if the output is varying a lot, that gives me the AC impedance. Okay. So that's the reason we use the current sources. Got it? Clear? Any questions? Okay. So and then so the pristine source we have for the current source, like I said, there are different ways. Band gap is not just one way. There's VT over R and different ways to do it. But for the current mirror, we assume that we get one clean source from somewhere, and we're just going to copy it very faithfully, okay, and then provide it. Because, as I was saying yesterday, that you have all different blocks, different chips all over the place, and you're trying to bias them with the same current, let's say, okay? So you're trying to create these small mirrors based on one source and just copy them, okay? And send them. And you remember why? Because I could send this voltage, this gate voltage or whatever voltage to all of them and tell them to copy it. Do you remember why a current is preferable than sending the voltage? Again, we spend almost like half hour explaining that. Why is current preferable compared to gate? I mean, sending a voltage. Like you remember you did a mirror. How did you do the mirror? You created a voltage by connecting the gate to drain. and then taking that voltage and providing it to other gates to mirror. Why don't I just take that gate voltage to all the circuits and you say, hey, you just take that transistor, put it in the gate and you'll get the current? What are the reasons? Yeah.
In the voltage, we take the noise to the other multiples. The noise will be repeated.
See, yeah, exactly. So you derived two small signal parameters yesterday. What were the two small signal parameters? GM and RDS, right? Now, when you do, you took a transistor yesterday when you did it, what was your GM value and what was your RDS value, roughly? So RDS was like almost, let's say 500K, right? And GM was what, roughly? So let's say 1 millisiemens typically, so 1e minus 3, right? So if I take a current and create a voltage and ship this to all over the place, right? And let's say far away, I have that transistor where I create that mirror, okay? Now let's say I have some noise sources which gets coupled because everything is a capacitor, right? Now let's say I have some delta V on this node, okay? What will be that delta V, delta I noise because of that delta V? It will be GM times delta V, right? The reason is you can follow the large signal model too. So you can do VGS plus 5 millivolts or 1 millivolt on it, find the current. But here, because the voltage is really small, I can just say, no, it will be roughly GM times V. There will be some error, but hopefully that error is small. Got it? Because in your small signal model, that's what you're doing, right? Basically, in your small signal model, you have VI, this is the drain, gate, and this is RDS, right? So this current is GM times VI. So if this is delta V, this current is going to be GM times delta V, correct? So let's say delta V is 1 millivolt, right? Or 10 millivolts. Then what will be delta I? 1e minus 3 times 10 millivolts is equal to 10 microamps, right? So you'll have a 10 microamp noise on this node. Got it? Now let's say I ship it the way I'm planning to ship. So I make the mirror right here itself, and then take this current and ship it to this amplifier. And then this node is still the same, right? So I have this cap and I still have a delta V noise, which is, let's say, 10 millivolt. Now how much noise will I get? Because now the noise is on the drain side. I have delta V over here. What will be the noise? It's delta V over RDS, right? Because now it's whatever is the voltage on the drain divided by the small signal impedance, because I'm assuming that signal is very small, right? And what is RDS? 500K, let's say yesterday we calculated, right? So delta V over 500K will be equal to what? 10 millivolt divided by 500K is roughly what? 5 times 2, that's 10 to the power minus 5. That's 20 nanoamps. Sorry. Just give me 1 second, okay? Okay, so is that clear why we ship currents instead of voltages now? Because the voltage gets multiplied by GM, which usually you want it to be a higher number. So it get multiplied and your current will be amplified if it is a noise signal, right? If you're sending it as a drain, and then that same voltage will get divided by the R out, which you want a higher number. So that means that noise current now will be much smaller. Okay? Make sense? Guess seems not convinced. See, you have to ask question. If you don't understand and you just go and start browsing phone, that's not going to help. I mean, you have committed to be here. Might as well spend that time here. Why are you wasting it? Right? You don't understand, just ask me, because I, went like half an hour on this, half an hour on the small signal, but looks like you guys are just not following it. You just have to ask questions. Doesn't see, I told you in the beginning of the class that it's important you understand what's being taught rather than, we completing it, because what will be the point? You spend 3 weeks here. Life is really short. 3 weeks is a really, current will change by like 10%, let's say. Okay. So that's why the matching is important, but we'll talk about that. Okay. So current source, everyone clear about it? All right. So, okay. So maybe what I'll do is I'll first, so now we want to create the op-amp. Okay. The one we want to design so that we can put it in the, that whole entire, microphone amplifier, create an amplified signal. So I'll just quickly draw a block diagram on what are the main blocks we need for the op-amp, and then we'll take a break and come back and start building at least the front end part of it. Okay. So for the op-amp, you've seen the op-amp circuits, right? So the goal is when you're creating these op-amp circuits and then some VREF here, the goal is like you need a really high gain here for a differential input, and you have a single-ended output which is proportional to this. Okay, so that's the goal. So the goal is you create, if I express it block-wise, what are the blocks needed for this? The first thing you need is this what's called a differential amplifier. So you have two inputs, let's call this VM and VP. Okay, and this output is just VM minus VP. So, I mean, VP minus VM, maybe some small gain, right? Small gain. And then the main gain stage is over here. The gain stage where we have, let's say, gain of A over here, right? So that's is going to be A times whatever previous gain you had, VP minus VM. Okay, so that's where you get the gain. And then finally, what happens is, see, this is a resistor, right? If I have a swing of 1 volt, let's say this resistor is 1K, I need 1 milliamp flowing through this. Where is that 1 milliamp going to come from? It's going to come from this guy. All right. So if I don't provide the output stage with that current, then this output will just collapse. Okay. So if this was 100 ohms, then I need like 1 volt swing and I need 10 milliamps, right? And that 10 milliamp has to come from this guy. Okay. So typically when you're doing generic op amps, you need a specific output stage. Okay. So typically it's called a class A, B output stage. And the job of the output stage is just impedance matching. So this guy has given you a lot of gain, but it can't provide much current to it. So if you have a really large load, like a really large resistance, then it will be able to provide it, but otherwise it cannot provide it. So you add another stage where the gain is just 1, but it can provide current now at the output. Okay, so that's really the basic kind of the block diagram. And then, you have all these bias currents you provide. So you have a biasing network. You have a biasing network, which, and in our case, it'll be just, and this is your V out. V out. Okay. So that's the output you're going to get. So that's this whole thing is what is embedded inside this. So you need a differential input and an output which is proportional to that differential input times gain. And then you have an output stage which can take that gain, also provide the impedance matching, which is, provide the current. And the simplest impedance matching is if you just take a transistor's gate and provide the load at the output at the source, whatever voltage you put, the transconductance ones we had shown, right? That current controlled, voltage controlled current source. The voltage controlled current source is what you can put over here, because whatever voltage you put, you can provide that much current for whatever load you have, as long as that voltage is matched. Okay, great. You got it? So, and there are a few definitions we'll just use. And one of the main reasons we use, obviously for this configuration, you need a differential input, but one of the main reasons we need a differential input is also to do with noise isolation. Okay, so typically the differential input Vd is expressed as Vp minus Vm. So that's the difference in these two voltages over here. Okay, then you have another term in this differential amplifiers called the common mode. Okay, so we call it VCM. I'll just write it in a different color so that it's more clear. So VD or VD differential is the difference in the voltage given at the input of the op-amp. That's VD. That's called the differential voltage. And VCM, or the common mode voltage, is defined as these two voltages divided by 2. Okay. So the common mode voltage, if I tell, oh, what's the common mode voltage? You add these two and divide by 2. And the reason you divide by 2 is because, let's say these voltages were same, then Vp plus Vm equals to, let's say, V, then it will become 2V, right? But actually it's just V, so you divide it by 2. And if one of them is higher by delta V, another one is lower by delta V, they get cancelled out, you get V. Okay, so it's just capturing sort of what's the common mode. Okay, I'll draw like a sine wave just to kind of show you what it means. All right, so these are the two sort of the main definitions of this thing. And if I show as the input, so let's say I'm giving, this is your Vi input, and this is time. And let's say this was my VCM. And then if I give, for example, a sine wave like that, and then let's say this is Vp, and then Vm, if I want to give a perfect differential voltage, I'll give it out of phase. So this will be Vm, right? So now if I take this difference of this, then the peak will be twice of that, and it will be a sine wave. And if I take the common mode, I take these two divided by 2, it will be basically that line. All right. Now, if I, let's say, ground one of them, so let's say I ground one of them and just give one signal, what do you get? You get a difference, which is that same signal, but you also get a common mode, which is that signal as well, right? Because let's say, for example, so let's say Vp equals to some Vp sine omega t, and then Vm is equal to 0. Okay, what's the differential voltage, Vd? Vp sine omega t. So it's the same as the signal, right? What's VCM? Will be Vp by 2 sine omega t, right? So that means you get a common mode signal too. Now, in an op-amp, you ideally want the output V out to be equal, if I take it common mode and differential, I can write it as some common mode gain times VCM plus some differential gain times the differential voltage. Okay. Now, every time you're saying the gain is 1,000, gain is 10,000, gain is 100,000, and so on, you're talking about this number here. Okay, because you don't want to magnify this. So ideally, you want this AD to be really, really high. You want ACM to be 0. Okay, so that's called the common mode gain, and this is called the differential gain. Okay, when we come back after the break, we'll start with the differential stage, and you'll see in that stage actually it provides you this sort of this inherent property of that gain. So ideally, you want ACM to be close to 0 and AD to be high. Okay, if you do that, then you can build op-amp circuits like this, because then any common mode here, it's not going to amplify output. It will only be amplifying any differential, because that's how you design these circuits. The circuits are designed here that any difference will get amplified. So that's why when you put the feedback, this node gets close to this node. But any common mode, if these two nodes are moving together, then you don't want to amplify that. And that also helps you with noise, because let's say you have a supply noise, right? Just like before, you have some cap which couples to here, you have another cap couple, the same cap which couples to both nodes, right? That node will come out as V noise on Vp, V noise on Vm. You add them up, divide by 2 times ACM, it will become 0. You got it? So basically that VCM will be this noise signal. If you didn't have this quantity 0, then the output will be your signal plus your noise also will be amplified. Okay, so that's the other reason people use differential amplifiers is if you have a noisy environments and you're carrying the two wires long wise, then you kind of cancel those noise as well. Okay, clear? So that's sort of the basic architecture of an op-amp and why you need differential gain and the common mode gain to be 0, because that's what is required for your op-amp circuits. And we'll try to build that with a simple differential amplifier stage. You got it? So what we'll do is we'll take this called the differential stage. I think people who have done analog, they're probably aware of it. And then we'll put a load on top, which is your current mirror load, and that should give you the output over there. Okay, got it? Okay, so let's take a quick break. And when we come back, we'll continue with that. All right, so we created an architecture we need for the op-amp, right? So we said we need a differential input, single-ended output, we need high gain, and provide some current. Okay, so let's start looking at how to build that. So we've already kind of looked at this common source amplifier, which gives us a gain, voltage gain. So now what we want to do is let's put two of them and see if we can get those properties from those two. Okay, so if I take two of them, in one of them I put the positive input, another one I put the negative input, and the outputs are obviously two outputs instead of one. So the output, I'm writing it as the subtraction of VOP minus VOM. Okay, how do we do it? We'll see that later on. But for now, just imagine there is a circuit which will take the output, convert it into single output voltage, which is VOP minus VOM. Okay, now VOM, if so let's say we have biased this with some current I. So the small signal parameters are GM and RDS, right? So this is GM, and let's say these are the exactly same amplifiers. So this will be GM, let me just write this. So this will be transconductance will be GM, output impedance will be RDS. If these are exactly same amplifiers, this will be, and biased same way, this will be also GM and RDS, right? So then I can write VOM. VOM is what? In terms of GM and RDS will be VIP minus VIP times GM times RDS, right? We got that yesterday from the small signal model. So, and you should always think about it, intuitively too. So this current is constant in an ideal current source, correct? So any voltage you give here, small voltage, the current here is going to change by GM times that small voltage. Now that current has, nowhere to go, but whatever is the output impedance, it's going to go into that. And that's the voltage which is going to get dropped by, right? So the current which is going to change in this branch is delta V times GM of this device. The voltage which is going to drop is whatever is the impedance of this output node times that current, right? That's so just always have that sort of this intuitive feeling on how to do this. Okay. So, and what is VOP? VOP equals to minus VIM times GMRDS, right? Got it? So that means if I want to do VOP minus VOM, that is equal to this minus minus will cancel, so it's GM times RDS VIP minus VIM. And this quantity I'm just calling V out. How we create this circuit, don't worry about that. So there is a circuit which takes the difference and creates the output. So that means V out is equal to GM times RDS times the differential input, which is great, right? That's what we want. We want a high gain. So we'll design it such a way that we get a high GM. So, 2ID over V on. So we'll make sure the current is high. And actually the current is low because it's GM times R naught. So 1 over lambda ID. If you expand that, you remember yesterday, it was inversely proportional to the V on and inversely proportional to current also. So you want actually very small current and the V on should be small because of GM. But obviously if you want high speed circuits, then that's not, then you have to increase the gain in some other way. So you get the differential gain, right? So this is the differential gain, which is AD, correct? This is AD, and we can design circuits to make this AD high. So that's one condition which is meant for us. Okay. Now let's look at the common mode gain. So actually, before I do it, let's try, why don't you try? What is the common mode gain? So common mode gain ACM is equal to V out, which is VOP minus VOM, divided by the input, and the input is VCM, and VCM is what? VIP plus VIM over 2. Okay, so use the same equations and see what this gain is. So just work it out, the equation, and let's see what that gain. So you remember the ACM, ideally we want it to be 0, right? We don't want any common mode gain. So any common mode, we want to just squash it. So that we want 0. So let's see what common mode gain we get out of this circuit. If we get the common mode gain to be 0, then we are good. We'll start with this circuit. If it is not, then we have to look for another circuit. Oh, actually, I forgot. When you're doing common mode gain, this V out is actually not VOP minus VOM. It's actually VOP plus VOCM divided by 2. Okay. So basically you don't want any common mode. I mean, obviously you want the differential output with respect to differential input to be 0, but that's called common mode rejection. The common mode gain is what is the input common mode to the output common mode. Okay, so I should write this one as VOCM. Or just write VICM and VOCM. So this one would be VOP plus VOM by 2. 2 times GMRDS. Okay, so basically you just take these two equations, right? You just take these equations and you do VOP plus VOM divided by 2. So if I add these two, this becomes minus of VIP plus VIM divided by 2 GM RDS, right? So then this VOCM over VICM is equal to minus GM RDS. So what do you see? You see actually your differential gain and common mode gain are actually the same, okay, which is obviously not what we want. So, so this is something we can't use for our op amp, okay? But a lot of times we still use this. These are called pseudo differential. So in the sense that it gives you a differential gain, but no, the common mode gain is still, high. All right. So this is a circuit we obviously can't use it. The differential gain is fine, but the common mode gain is the same too. So the differential is GMRDS, which is really high, but the common mode gain we want it almost 0, and that's still high. Okay. So makes sense? Got it? All right. So any questions on this one? So just going by the definition, taken this circuit which we already had, we just made copies for the negative side, we made it for the positive side, and then we're just trying to measure the uh, the differential gain and the common mode gain. Okay, got it? Makes sense? Okay. So now let's see. So can anyone suggest now maybe we can make a change to this circuit to, so the differential we want still the same, but the common mode we want to reject, in a sense if there is anything moving in the same direction. See, because what's happening is this node, even if I go like this, it's still delta V times GM times R naught, which gets to the output. If I do this, it's still with respect to ground. That's the problem. Okay. Now, if I can do something where I move up, this also moves up. And if I move down together, this moves down together, that is what will reject it. Okay. So before I show how to reject it, I'll show you another. So what you have seen is this common mode amplifier, right? I'll show something what's called a source follower. Okay. So source follower, and that will kind of give you an idea on how to do it. So we'll look at a source follower amplifier now. And it'll be clear why it's called source follower. Okay. So now if I have the same, and let's say this is connected to VDD, but my current source is now, the bias current is actually on the source side. This is still an NMOS. And let's say this is VI and this is V out. Just looking at this circuit, can you figure out what will be the relationship between V out and VI before we do small signal gain and all that? And yeah, the bulk is connected to ground. So now you see the source voltage will actually be higher than the bulk voltage, which means that this VT will be higher now. Okay. But what's the relationship between V out and VI? Relationship in the sense, do you think V out is going to follow VI, or it will be a gain, positive gain, or it will still be a negative gain like the previous one? What will it be? So, let's start with something. Okay. So let's say this is 1.8 volts. Okay. Find my cursor. So let's say this is 1.8 volts, and let's say this was halfway through 0.9 volts. Okay. Now just forget the source to bulk part of it, and the VT is for our for technology we found out what. So let's take that same one we had yesterday, 4 by 1 micron, and let's say this was 50 microamp current. Okay. So then what will be V out? 50 microamp times RDS. No, just forget the small signal now. DC bias. So this is like you're thinking about DC bias right now. So the input is sitting constant 0.9 volts. You have a VT of 0.5 volts and your neon Cox, I think we calculated what, like 300 microamp per volt square yesterday. So that's, and the size is 4 by 1. So what is going to be this voltage? I mean, you can express it as just variables too. You don't have to actually put numbers. But how would I go about calculating this voltage? And assuming obviously this is in saturation. So I assume this VDS is greater than VGST. It may not be the case, but we assume that, first find out. If it is not, then we go back and change the equation. So if, let's say, if it is in saturation, what will be V out for 0.9 volts? Say that again. I mean, you can just express it. So you remember I always told you, like when we started it, when it's always good to express VGS as what? VT plus the VD sat term, V on, that's why it's called V on, that's the extra term, right? So just write the equation, right? If you write the equation, ID is equal to mu n Cox over 2 W over L VGS minus VT whole square, right? And if you rearrange this term, then VGS is equal to VT plus so root over ID times mu n Cox over 2 W over L, right? So ID, 2ID, mu n Cox, W over L, root over. And this is the VDS term, or VD sat or V on or V effective, whatever you want to call it. Okay. So the idea is you need at least a VT plus some delta V to accommodate this current for the size you have, for mu n Cox you have, for the current you're flowing. Okay. So for example, let's take the numbers we have from yesterday. So VT is what? VT was, let's say, 0.5 volts, right? 0.5 volts, and the current is 50, so that's 100 microamp, right? And I think mu n Cox we calculated was what? 300 microamp per volt square? Or let's take 300. I mean, this is just for calculation. Or let's take 200 microamp per volt square. I forget what the term was, but let's take that. And then W by L is 4. Okay. And then we take the square root of this. So this is roughly what? 100, 1 by 2, 1 by 8 microamp cancels volts. So 1 by 8 volts is what? It's about 0.125 or something, right? So this will be roughly about 0.625 volts, let's say. Got it? Makes sense. So if this was right, let's say this was not 200, 300, doesn't matter, it'll change it a little bit. And VT is, let's say, 0.45 or something. So this might be 0.6 volts. So let's say this is 0.6 volts, okay? So this is 0.6 volts, let's say. Okay, so now tell me, what should be V out? Say NMOS. Just if you're getting confused, just plug the values, do a KVL. That's it, right? You just put a KVL around this loop. So initially, if you're having, so this is 1.8, you just put a KVL around this loop. So 1.8 minus VDS, oh, actually, sorry, we are doing VGS, so you put a KVL around this loop. So you have 0.9 volts here plus VGS divided by this, whatever it is, that should be equal to the total voltage. Okay. So what should be this voltage here? So V out, 0.5 minus VGS is equal to V out, right? So 0.5 minus VGS minus V out is equal to 0. Got it? So 0.9 minus VGS minus Vout equals to 0. So VGS will be, Vout will be equal to 0.9 minus VGS, right? Vout equals to 0.9 minus VGS, which is 0.6. Oops, sorry. Where did it go? Yeah. Got it? Because, see, this VGS has to be positive. If this is 0.6 volts, this node has to be 0.6 below 0.9. What is that? 0.3? Got it? So this needs to be 0.6 below 0.3. So that, 0.6 below 0.9. This is 0.3. Got it? So that's how you calculate VGS. Make sense? Now, if I change that to 1 volt, what will be the output now? So let's make a table. So I'll call this VG, and this is V out. So I had 0.9 volts, output was 0.3. And let's say now I make it 1 volt. What's the output? 0.4, right? Because it is not true, but at least with this calculation, it is still 0.5, still 100 microamp. This is still 200 by thing, still by 4. We kind of approximated this. So VGS is still 0.6, which means that this will be 1 minus 0.6, which is 0.4. Okay? 0.4. If I make it 1.1, 0.5. If I make 1.2, 0.6. So now you know why it's called source follower, because source follows the gate. But in reality, what happens is this VT is a function of VSB. But VSB is changing, so this will change. So it will not exactly follow, but it will almost follow it. Okay? So that means whatever is the gate voltage, the source will just follow it. Okay? If it was an ideal one. And you can actually connect the gate to source voltage here, and then the VT will not vary. And that's a lot of times we do that, except that the source and the capacitance will just be connected to that. Got it? So this is why it's called source follower. Okay, so let's do one quick exercise right now. Draw the small signal for this one. Okay, find out V out versus Vi small signal gain. Remember the small signal, how to make the small signal model? What are the 2 steps? Make all the independent sources 0. So this will become a short, this will become an open. Substitute the nonlinear model with the linearized model of this guy, right? So remember the linearized model for the transistor. So transistor, we are ignoring so this is gate, source. So this will be VGS, and this current is GM VGS, and then you have RDS, and that's drain, right? So you take the gate, source, drain, substitute with this model, make the independent sources 0, and for this circuit, calculate V out over V in. Small signal V out over V in. Okay, so obviously it will be in terms of GM and RDS. By the way, this is small signal. So there is no VGS or VDD because all the DC part should all become 0. only what I'm varying small signal should remain, everything else should just drop off. Okay, so this V out over V in should only be in terms of small signal parameters, small signal, and if you have obviously resistors, right? Resistor small signal model is still R. So if you have a R, small signal is still R. But here there is no R, so I mean the output impedance of this guy, but right now we are considering it as an ideal source. Okay. Yeah, so this will, open, this will become a short, so this end will become the ground, this will be your gate to, uh, the source is basically where your V out is, right? So, and the drain is where it is ground. So that's why I'm saying you just take, so when you short this, this becomes ground, that's your input, this is your output, and that's it. So you substitute that and then find out V out over V in.
Positive GM and because the drain is sorted, drain is grounded, V out is the source.
Yeah, just do it. I mean, first of all, if you are convinced what we just said, right, that the output will follow input, then the V out versus V in should be what? Should be 1, small signal, because if I change this by delta V, this changes by the same amount delta V, and it should be positive, right? If you're getting another number, RDS times GM, you go back here and see if something doesn't make sense, or you have to fix this one. You got what I'm saying, right? So you biased it and I change it by delta V. This should change by delta V because that's what I've seen here, large signal wise. So the small signal model should also give you that same result. If it is not giving you, either you go back there and say, oh, that doesn't make sense, we have to fix it, or you go back here and fix it. You got it? So small signal gain is like, I've been saying it's an incremental gain. I bias it to some extent. I change it a tiny bit higher or lower, and the output, does it change by higher or lower, and by how much time? Does it change by a scaled amount? Like for the common source PET, I change the delta V by small amount, the output drops by a huge amount. Okay, so that is the negative gain. Here it actually follows, that's what I've seen. And ideally, let's say the bulk was shorted to source, it will actually follow exactly, which means that the small signal gain should come out to be 1. Okay, so see if that comes out to be 1. Okay, so the small signal for this one, actually, unless you have a load, it's a little bit counterintuitive to see. But if you see the small signal, it was a gate to source, and this is equal to GM VGS times RDS, right? Now your drain is ground now, small signal ground, and gate is your input with respect to drain now, because that's the ground now. Okay, and the source voltage is with respect to this, but you cannot have any current flowing through this, because if you have any voltage across this voltage will result in GMRDS, which is higher than what you require. But there's no current for it to flow. So that means this gate should follow the source. If it doesn't follow, then you'll not have an output which matches the source, because if it doesn't follow over here, then that times GM VGS should flow in over here, and that's not true. So that's why the gate and the source has to follow. But in reality, you always have a RDS which is from source to ground, right? So where is the source? Yeah. So this one to ground, well, it's in parallel here. So VI, 1 second. Yeah, that's also, so this is RDS1, this is RDS2, and this side is ground here, and that's your VI. So
It will be VGS minus VI minus VO.
yeah, I think that the sign is fine, but basically you put a KVL around this loop, and then this is GM times VGS times RDS. This is minus. So V out 1 plus 1 over GM RDS is equal to VI. Okay, so yeah, if you're getting confused, you just write the KVL around this loop. So your VI plus, so this node from here to here is VGS. From here, this is VGS. So you write the KVL loop here. So VI plus VGS is equal to GM times VGS times RDS is the voltage dropped across this, right? So I just write that. But instead of expressing V out as GM VGS, I want to express in VI and V out. So I make VGS equals to V out over GM RDS. So that's GM, because this current which flows into, because there is no other place to flow. So whatever current is flowing here has to go through RDS. Got it? So that flows through that. So if I expand that, I get this, right? So I get 1 plus 1 over GMRDS, and you want this GMRDS to be really, really high, right? So if this is high, this turned out to be 0, and then V out equals to VI. Okay. But in reality, if you don't have the bulb connected to the source over here, it will be connected to ground. Then you'll have a GM VGS also that will come into picture, but we can ignore that for now. Yeah. But you just look at it from a large signal, you know that if I increase this by some delta V, this node has to follow that for it to remain in saturation. Okay, otherwise, because if this node doesn't follow, then this current will not match this current, right? So for example, we calculated that this should be 0.6 volts for this current to be equal to 50 microamps, right? Now I raise the voltage by, let's say, 100 millivolts. If this doesn't change by 100 millivolts, this current is now higher than 50 microamps. Now where is that extra current going to go? There's no place to go, right? So this voltage has to go up till this ID becomes 50 microamps, and it will go up by again the same amount as this because I need the VGS still to be 0.6 volts. Got it? So that's why it's a source follower. And small signal, if you do it, like I said, it should come out pretty close to that because you have a finite output impedance, so it won't exactly follow, because this one will go up to the point where it is following that curve, right? If RDS was infinite, then this term will become 0, right? Ideal RDS is infinite, then this term will become, if it is not infinite, then it will change by some amount. You got it? Okay, so just at least intuitively you follow that, right? Now, so that's what's called a source follower amplifier. Source follower is basically, it follows the source. So there is no voltage gain. But can you tell me what's the advantage of that stage? So it's not giving me any voltage gain, but it's a very popular stage we use. In fact, in the op-amp architecture I showed you, it's used, we use what's called class AB most of the time in high power, but we use this stage a lot. What advantage does this give me? If this current is really big, I can put a small resistive load and it will provide that load current without changing this voltage much. So that means this input can draw no current at all. I change the voltage. So let's say I get the voltage gain, but I can't provide current to a resistive load. Then I can use this stage. Okay. So that way I get the voltage gain here. The current is provided by this guy. So that source follower, this is the impedance. So it converts a high impedance node to a low impedance node. So if you see in this architecture I was showing. So first you created this differential to single-ended, then you created a voltage gain, and this output stage, that actually can be one of the output stage, but it's what's called a class A output stage, which means that it is always drawing current. So let's say you want to provide 10 milliamp to the load, then you always have to draw 10 milliamp in that branch, which will be wasting power. So for example, you're using a phone or your power amplifiers, let's say for the speaker. Typically, if you don't put music or you're not uh, uh, giving any sound signal to it, then the power drawn is very small. It's only when you apply music or apply voice or signal to it, that's when you get the power. And for that stage, that's not true. It is always drawing power, even if there is signal, no signal. So this class AB stage is where you actually draw power only when there is signal. Otherwise, it just draws some quiescent current and stays there. Okay. So that's actually a output stage. A lot of times people will use it. I don't know why I went there. Okay, clear? Now, hold on a second. I think I messed up the slide somehow. Okay, so with that in mind, so what do you think I can do here now to modify it so that way I get the common mode gain to be 0, differential gain to be this high, because that's my requirement from this thing. So now, having known how the source follower works, what do you think I can do here? I think people who have done analog, and they probably know by now, but those who haven't or those who have forgotten analog, can you maybe tell how to modify this. So you remember what the problem is with this circuit, right? Differential, no problem. I get the gain because I give some positive value, this goes down. This one, I take it down, this goes up. I take the difference, I get a really high gain. That's really good. But the problem is I start changing the common mode. This also changes hugely. So if I have some small common mode, the output will get saturated. And I don't want that, right? I want, like, for example, you take an op amp. The voltage follower mode in op amp where you take the output, connect to the negative, positive, you give a V in, right? What's the output? V in, right? It just follows. But the common mode is what? It's V in. Because if this goes by 1 volt, this common mode is also going by 1 volt, right? If I use this circuit, the output will get saturated. It will just go out. The common mode also will change and it will get saturated, right? So what can I do over here? So obviously I didn't invent this, but the popular one is you basically take that same circuit you had before, and we'll change that R later on, but let's first find out. Now what we're going to do is we're going to give the bias current from the source itself. Okay. So if we do this, then what will happen is when the voltages are same, and let's say the sizes are exactly the same, then this current has to go half here, half here. Correct? Why? So if this voltage is same, this current has to go half here, half here if the sizes are exactly the same. Why? Here? No, this one is okay. Forget the resistor for now. Let's just connect it so that we'll just measure the I here. So let's say this is VIP, VIM. Okay, so this will be, we'll call it I. This is an output is the negative side. So, well, we'll call it IP and IM. Okay. So, and let's say this is the bias current. So we'll call this IB. So what I'm saying is that if VIP equals to VIM, then IP equals to IM equals to IB over 2. Okay. And the question is why? Why is that? And this obviously under the condition that it's the same. So whatever transistor you have here, this is W over L. This is also W over L. So why does the current split between these two? So I assume both of them are in saturation. Okay. Yeah, go ahead. No, yeah, symmetrical. Obviously from symmetry you say, yeah, it kind of maybe splits. But then from the current equations, how do you prove it? Like, so an assumption is there in saturation. Okay. In linear also it'll be true, but let's say it's saturation. So in saturation, what's the current equation? Mu n Cox VGS minus VT whole square, right? So if I write IP equals to mu n Cox over 2 W over L VGS minus VT whole square, right? What's IM? Mu n Cox over 2 W over L VGS minus VT. Well, this is VGSP minus VT square. This is VGSM minus VT square, right? Now, this is same, mu n Cox is same, and I plus Im is what? Equals to IB, right? So, IP plus Im equals to IB, correct? Now, Mu1 Cox is same, W over L is same, Vt is same. What about VGSP and VGSM? What is VGSP in terms of VIM and source voltage here? So let's call this Vs. Let's call this node VS. Let me just change the color to be. So this is VIP, VIM, and this is VS. So what's VGSP? VIP minus VS. What is VGSM? VIM minus VS. And what's the condition? That VIP equals to VIM, because these two are the same voltage. If VIP equals to VM, then VGSP is equal to VGSM, because VS is the same node, right? It's the same node which is shared by the two pro. Then VGSP is VGSM, then I plus IM has to be ID by 2, because this is just 2 times IP or IM equals to IB. Follow? Right? So this is with the equation, but intuitively you should understand too, because what I can do is, if this voltage is same, I can take this and flip it here and just make this 2W over L. If it is 2W over L, the entire IB is going, and I take one transistor out, there should be half the current in that. Got it? So because this VGS is exactly equal to this VGS. So that means this current has to be exactly the same as this current. So if the two currents are same, then there has to be IB over 2, IB over 2, otherwise they will not work, right? Got it? So that's when this is same. So let's say I started with 0.9 volt, like I said, right? So 0.9, 0.9. So this is 0.9 volts. This is 0.9 volts. So what had we calculated this to be in that source follower? 0.3, right? Let's say IB is 50 microamp. So in that source follower, we had calculated, sorry, this has to be 100 microamps. So in that source follower, we had calculated that, let's say this was 4 by 1, these were two NMOSes, then for 50 microamp, this will be 0.6 volts. So if this is 0.6 volts, this is 0.3, right? So 50 comes from here, 50 comes from here, that's 100. Got it? This is 0.91. Now I raise these two equally to 1.1 volts now. This is 1.0 volts, 1.0 volt. What happens to the source now? It has to be 0.4. First of all, it's the same node, right? If it is the same node, VGS is the same. That means the current has to split. If the current splits half-half, it has to be 50. If it has to be 50, VGS has to be 0.6. VGS has to be 0.6, that becomes 0.4. Okay? So that means this current did not change even you are changing the input voltage, common mode voltage. Okay? If that didn't change, current didn't change, then if I put a load here, then this output also didn't change, because that output is VDD minus IR times, IP times R. So which means that I'm changing this, but this output is constant, it just stays same. It will only change if I start giving a delta I over on both sides. Got it? So that's what this thing does. So this current, where you short the source side and give the current, it actually rejects your common mode. So your common mode gain is 0 now. Ideally, it is 0 right now. You got it? So now you have to find out if the differential gain is like old times or it changed. Okay? But the common mode gain, at least we now, is 0, and that's what we wanted. And if the differential gain is the same as before, GM times RDS, then we are all good, right? And that's the stage we can use.
One more resistor. RDS bundle are there.
Yeah, so right now I'm assuming this is the dominant load. So let's say this was really high, then this will be parallel, but let's say this is the smaller node, then that that will dominate it. Okay, so but I'll give you a quick. So let's. All right. So before we do this, let's. You can work out right now. So let's start with a new one. So forget the load. What I want you guys to do now that you hopefully you're convinced. So this is some current IB. Well, I'll call it 2 IB. So that means when VIP and VIM are same, then you have IB flowing in this, IB flowing in this. Okay, so don't worry about the load and all that. But let's find out what happens to the current so we'll call this current IP and IM. Okay, so what you want to draw is, so let's say this is IP IM and this is VID, which is VIP minus VIM. Okay, so when VIP minus VIM is equal to 0, means these two are the same voltage, what happens to in the two branches IP? So let me switch to, let's say I make, so I'll use blue. So let's IM be blue and IP be red. So IP be red. So red is IP, IM is blue. So what will be this current here? So both of them will be IB, right? That will be IB. Okay, so if VIP equals to VIM, both the currents are IB. Now let's say I start increasing VIM or VIP in this direction, okay, and VIM in the other direction. The current will be more in this branch and less in this branch, right? So for example, let's say I add a delta V here and minus delta V over here, then whatever current gets flown here, that same current will get subtracted here. Because, if you look at it small signal wise, delta V by 2 times GM will flow in this direction. Delta V by 2 GM will get subtracted from here because the total current still has to be IB, correct? So let's say I go positive side where VIP, some delta V over 2, okay, or VIP minus VIM is V. So which means that I'm going one side delta V over 2, another side I'm going delta V over 2. So that the common mode is still the same, just you're changing the differential, which means that IP will go up or go down? Will go up, right? So it'll go up in this direction